All right, so we start with a review of what we discussed in the last lecture. We use local algebras to reformulate locality or strong notion of locality as additivity plus Higgs duality, right? In this sense, a truly local theory has no global or gauge or generalized symmetries. We define what R-form symmetries are. So these are theories that they have operators, non-locally generated operators for regions with non-trivial pi of R, fundamental non-trivial Rth homotopy group, right? The example that, and then twist is the non-local generated operator associated to the causal complement region, which has non-trivial pi of D minus R. But the example I want you guys to have in mind is 4 dimensions and gauge theory. If this language is way too formal, what I want you to have in mind is 4 dimensions and gauge theory as a theory with one form symmetry, right? And this is for you to know where it generalizes. So the 0 form symmetry is global symmetry, right? And it goes actually, when you insist on a local description, what you actually do is the following. In a 0 form symmetry, you put degrees of freedom at each point space-time. In a 1 form symmetry, you have a Wilson loop that's non-locally generated. You split it into tiny regions, and you put a degree of freedom gauge field on one cell, a line, an interval, right? That's a connection. Now you can see how the generalization goes. In higher form symmetries, you have higher dimensional objects. Like, for example, 2 form symmetry would have surface operators, right? And then the surface operator, to come up with a description that's local, you would, if you want to, for example, to come up with a lattice description of it, you totally can. You would put a degree of freedom for a space on the lattice, right? So you would associate degree of freedom living on the face. Good. All right. So, but we're discussing electromagnetism in 4 dimensions. We discussed electromagnetism in 4 dimensions as a U11 form theory with a U11 form symmetry. So, as we said, we have to look at regions with non-trivial pi 1. What is a region with non-trivial pi 1? It's a torus or donut. It's a donut. Sorry. Now, there's a Wilson line. So it's a donut. There's a Wilson line that goes inside it, right? These are non-local operators. Sorry, Wilson loops, non-local operators. Why? Because if you take the donut and split it in half, there's no way of generating this guy by putting together the Wilson loops of these guys. All right, so there's a brand new operator. If you have heard of the story of edge modes is again the story of insisting on locality, right? So the idea of edge mode is that you have a theory with this Wilson loop that is non-local, right? You say, I'm going to generate this. If you cut it, of course, this is not going to be gauge invariant, but it will be gauge invariant if you do it this way. But this means that the moment you cut it, you have to introduce degrees of freedom here. You have to put a chart. Otherwise, this will not be gauge invariant, right? That's what the story of edge mode is. Again, that's something you obtain when you insist on local description. You don't have to do that. Okay. As you can tell, there's something very, very topological about this story. All right. Now, this is the intertwiner. What is the dual? These guys come with, there's always a dual operator. In this case, it's the Dirac loop, right? It's an operator that points to the failure of duality for the causal complement of a donut, which is a donut turned inside out. That doesn't mean much if you know what I said. Okay? All right. Now, the not so we discussed what these guys are. They're again loop operators, and the loop is you're integrating something. So there are two ways of describing this. If you insist in a description of this in terms of a mu, right, the gauge degrees of freedom, then that corresponds to non-single valued gauge transformations, right? So there will be singularities associated with this. We talked about how to think of the Dirac loop in this language, right? Or you could describe this as, in terms of the dual field, A tilde, as just a Wilson loop for the dual field. Now, what is a dual field? Oops. Here's to define the dual field. So you have the A mu. From A mu, you define field strength. From the field strength, you calculate this. You contract it with the covariant 4-index totally antisymmetric tensor. This is what it means to talk about the Hodge dual in flat space. So this is F tilde. This is also two form. You can see it's easy to see that this is totally antisymmetric because this guy is totally antisymmetric, and has two indices, so it's a two form. And this could also be viewed as as D of some one form, which is the dual gauge field. So if you take the dual gauge field integrated around this, it's an equivalent description of the so-called Dirac loop. We said more things, but I'm not going to repeat them all because we have to move forward. Questions? We talked about Dirac quantization condition. We talked about a whole bunch of things. All right, so we're going to completely change gears. If there are questions, ask. Yes. As opposed to
as a loop of perpendicular to the like geometrically.
There's some homotopy theory there. So you have to the homotopy has to do with non-contractible circles. So pi 1, which is the so-called homotopy theory, the fundamental group has to do with loops that could not be contracted. If you have a donut, the only loop that you have that cannot be contracted is this loop, right? Now, here, consider the complement of donut, the space outside of a donut. The non-contractible loop is this guy. Good. This is the only topologically, it's the only non-contractible. I shouldn't say homotopy theory all over and over again. It's just a fundamental group. Loops that could not be contracted, right? In your homework, you'll see that it's only for there's a reason that gauge theory, you've heard about it all over the place. Like it's all over the place and it's complicated. Whereas higher form symmetries, you haven't heard much about it. Well, there are gauge theories out there. That's one thing. But one important distinction between them that you're going to discover in your homework is that it's only pi 1, the fundamental group of this that can be non-abelian. All the higher homotopy groups are abelian. So this adds another level of complication to the story, but this is just for you. One of the homeworks that your homework problem is to show that higher homotopy groups are all abelian.
Yeah. Does this have to do with like 2+1 being a break group at all? No.
This is a general statement and for an arbitrary surface in arbitrary dimensions. Okay. All right, we move on. We're going to completely change gears and talk about something else. Well, go back to everything we said before. So what did we do? A huge part of this course so far has been trying to build explicit examples of four-dimensional quantum field theories. We achieved that using symmetries. There are two classes of such theories. One we discuss in more detail, one-form symmetries, gauge theories. And then there's another class, these are conformal theories. These have scale invariance. We did not discuss them really in honest to goodness description of them. We just discussed the trivial Gaussian fixed point. But conformal field theories could exist in 4 dimensions, period. And they both rely on a lot of symmetry. But an interesting thing about them is that, well, okay, why are we constructing such theories? Because we want to describe nature. This is not just like some fun exercise in mathematics. We're physicists. But here's the catch. Both conformal theories, conformal symmetry, and one-form symmetry, gauge theories, forbid mass terms. This means that if these are to be used for modeling nature, we're going to struggle with mass, explaining mass. Looking around in our 4-dimensional world, we find lots of massive particles of different mass, right? We just do all sorts of experiments and Poincare representation theories in terms of mass and spin, and we just discover these particles. And they all have different masses. The only massless modes that we know are photon. What else? Not Higgs. Gluon. What else? Graviton. That's it. Right? And they all have to do with long-range forces. They're all gauge theories. Right? These are the gauge theories that we do see gauge theories. They've survived, except that we don't really see gluons, but we'll discuss that actually. But then when you look around, there are so many degrees of freedom that are massive. Right? How do you describe them? You could say this is okay. All right. Are these quantum field theories that we've discussed relevant for real world? And the idea here is hidden symmetry. So what is hidden symmetry? It's a theory that's symmetric, but not real. If you want to use these models to describe nature, it turns out that there could be 3 ways that we could use these symmetric descriptions to describe nature. It could be that there is an approximate symmetry. Some terms in the action satisfy the symmetry, and some explicitly break it. But if the breaking is small, you could do perturbation theory. What is the example of that? Perturbative quantum field theory. What is the perturbation theory in? Around the conformal fixed point. So you have a theory that has is massless. Well, the theory is conformal. Then you consider another theory, which is that conformal field theory, plus some small terms, some terms that explicitly violate it, right? But somehow, for some reason, they're small. And then you construct the machinery of perturbative quantum field theory or perturbative conformal field theory. Sorry, perturbative conformal perturbation theory to describe your theory. So that's one use of explicit. This is called explicit symmetry breaking. There are many examples of it. Or you might have spontaneous symmetry breaking. We saw examples of this in the ON model. But what is this? When the laws of nature are symmetric, but the nature is, so it's not just a theory when we're describing nature, we're also given a solution, right? The solution we're given doesn't respect symmetry, right? Laws of nature, F equal ma, laws of nature are rotation invariant. This room certainly is not rotation invariant. This room is a collection of excitations, right? It's a solution to the equations of motion. There's like chunk of matter here, chunk of matter there, chunk of matter there. The equations are rotation invariant, however, this room is not. The solution is not. In principle, that's not a big deal. Of course, the vast majority of states of the Hilbert space will not be symmetric. We are particularly interested in the case when the vacuum does not respect the symmetry. But that is really the context of spontaneous symmetry breaking. Did we discuss Goldstone boson? Okay, we did talk about that. We saw that there will be massless modes and Goldstone boson coming every time we have spontaneous symmetry breaking. Good? Yeah.
What is the term accidental symmetry?
Accidental symmetry. Can you guess what it is?
I know what happens in the UV.
So accidental means what? Means that so think about your normalization group flow. The UV theory, when we say accidental, you're kind of dismissing it. It's not a true symmetry of the theory. So the UV theory doesn't have the symmetry. You run the RG flow in the infrared, you somehow end up with a bunch of degrees of freedom, right? That approximately have a symmetry. You call that accidental symmetry, right? What's an example? Well, you could call it accidental. That's not the most rigorous terminology. It's an emergent symmetry. That's what it is. It's an emergent symmetry, right? Accidental symmetry is sort of like an emergent symmetry, right? Because whatever like the logic is that we like symmetries to insert into the UV Lagrangian when we build our local quantum field theory because it protects the running towards the infrared, right? If this is something that's really only comes out in the infrared, right? So it's not really guaranteeing the niceness of it. But what are some examples of these? You know quite a few. Yeah.
Is CP even a QCD one? Is there something specific?
Much easier than that. Every time I mean, think about the idea of quantum field theory in the infrared, right? Quantum field theory as describing the long wavelength regime of some spin model that has gone critical. Quantum field theory has relativistic invariance. Deep in the infrared, you might have even conformal invariance, right? None of that is present on the lattice. This is emergent. We saw explicit an example of this in lecture 1 or 2 of QFT1. We took a bunch of masses and connected them with springs, right? The UV degrees of freedom were non-relativistic and massive. In the infrared, we got the theory of phonons. Deep in the infrared, it was relativistic, right? Boost is emergent over there. Sorry, now I just went on a tangent, complete tangent. Spontaneous symmetry breaking. That's what I want to talk about. But there's something nice about spontaneous symmetry breaking. Spontaneous symmetry breaking also gives you massless modes, right? Okay. Then there's another option. There could be that there is a symmetry deep in the UV, but that is hidden. You don't see it because as you run towards the infrared, the theory gets strongly coupled and complicated, and you do not see that UV symmetry, right? It took us a long time to learn about, QCD, right? And one extreme example of this is confinement and pions, right? We said that confinement is a phenomenon that all the finite energy excitations are neutral, charge neutral, right? There's no way for you to see what the UV symmetry is unless you push to really, really high energies. Another example, chemistry, right? In chemistry, there's hydrogen atom and a bunch of atoms as fundamental degrees of freedom. An atom, hydrogen atom, think about that. If you can't resolve what's inside the hydrogen atom, or if you don't have enough energy to kick an electron off of the hydrogen atom, how would you ever know about charge? Right? Because you cannot separate one of them. You would work with effective degrees of freedom. But so there are these three possibilities that tell you about how your UV theory might have a symmetry, and that means that the theory is well defined, but the infrared you don't see it. Okay? And in all these cases, as you go to higher and higher energies, the symmetry is restored. Right? Conformal field theory, the perturbation that you made is relevant. So you go deep in the UV, scale invariance is restored. Right? Spontaneous symmetry breaking, why is it restored? because the potential has this dip, like a simple example, the potential looks like this. High up there, you see that it's Z2 symmetric, right? It's only below this energy scale that you have spontaneous breaking. And then, of course, UV symmetry is, gluons. If you go deep in the UV, you'll discover them. All right? Questions? Okay, so we did discuss spontaneous symmetry breaking for global symmetries. Not really. We said a few things about it. We're going to go over it again. But now, what I want to say is the following. What we see in nature is we see massive gauge bosons, or we see massive vector fields. That's what we see, right? Examples of those are the W bosons and Z bosons, right? We see them in nature. And gauge theory is going to struggle to produce that because non-abelian gauge theories, the gauge boson must be a massless vector field, right? The gauge invariant tells you that massless gauge boson should have 2 degrees of freedom. If it's massive, it will have 3, right? The gauge invariance makes sure that there is no degree of freedom in the direction of the propagation. That has been the working principle for us, right? So you can't have massive vector fields as gauge bosons. Also, much worse than that, if you don't know anything about gauge theory, massive vector fields have poor UV behavior. That's just a statement. If you try to quantize massive vector fields, you're going to have a hard time. Now, spontaneous symmetry breaking in gauge theories was this discovery that in the low energy, you actually end up with massive vector fields that have good UV behavior, because deep in the UV, the gauge theory is restored, right? And the UV behavior is generated by gauge invariance. Now I can actually explain what is meant by spontaneous symmetry breaking of a gauge theory. One thing that you might find mysterious is the following fact, that all along the course, up until past 2 lectures, I was saying that gauge theories, there is no symmetry. There's no symmetry. It's just a redundancy. So if it's a redundancy, what are we breaking? Right? We are breaking one-form symmetry. That's what we're breaking. Physically, we're breaking one-form symmetry. Okay. What happens is the following. In gauge theories, when you break the one-form symmetry, your gauge boson becomes massive. What is the consequence of that? If photon had a tiny mass, how would the universe change?
It was a short range field.
It would be a short range field. What does that mean?
It's not 1 over R squared.
Exactly. It's not 1 over R squared. So what would it be if it had a tiny mass? No. How's the behavior? You know it. A massive mode. We quantized massive scalar fields. What was the 2-point function? It falls off exponentially, right? It's e to minus mr. It has to fall off exponentially. If you see a power law, that means a conformal field theory, right? And the massless free mode tells you it's 1 over R squared. That's exactly where it comes from, right? When we quantize, if you recall how we did, when we quantize the electromagnetic field in a particular gauge, I forget which one we use all sorts of different gauges. In some gauges, it looked like 2 components of scalar field, 2 component scalar fields, and scalar field by dimension counting. We can see what the 2-point function behaves like. Good. So it's not that the mass of photon could be teeny tiny and we would not notice it. tiny photon mass means something absolutely dramatically different, right? We talked about this in word identities. The fact that word identities don't give quantum loops don't give mass to photon is absolutely crucial. Otherwise, that will ruin the whole phenomenology. The universe would not have a long-range interactions, right? We would never see photons that were released from CMB, right? We would struggle to explain those things because these guys have been traveling for billions of light years. Yeah. All right. Do we see massive gauge bosons elsewhere in nature? Yes. Can photon be massive? Photon, as we said, it cannot be massive. But if you're saying that spontaneous symmetry breaking can it can effectively give a tiny mass of photon, the theory goes from long range to short range. I'll explain that. We've seen this in some states, right? You put the theory in some background, and the photon will acquire effectively a tiny mass, which means that in that medium, the evolution will not be 1/r squared. The 1/r squared law would not apply. Example, do you know? Well, I wrote it here. Superconductivity. That's what it is. I'll explain it. So historically, this problem was simultaneously solved in condensed matter theory as BCS theory, and well, I don't know simultaneous. BCS is probably older, and also in particle physics. Okay, so to go over this, I have to first remind you what spontaneous symmetry breaking and global symmetry is. Consider the ON model. We did this calculation. So the Lagrangian density is del mu phi a squared plus half mu squared phi a squared plus minus this. We did this calculation with a minus sign here to calculate the effective action, right, at one loop, because we're after calculating the beta functions of the ON model. If this is minus, you do not have spontaneous symmetry breaking. Why? Because both of these terms are positive, so there's no cancellation, right? You only have one solution, and that is phi 0. If there is a sign difference, then the phi 4 and phi 2 are competing, so you end up with a funny situation where you could have non-trivial vacua, which is not phi equals 0. So in the ON model, we talked about breaking spontaneous ON symmetry. So ON symmetry is realized by these ON matrices. For example, O2 could be broken to just like fixing the vector, and there's this Mexican hat potential. All right. So when you do this for the ON model, I'm breaking ON to ON minus 1 by giving a VEV to vacuum expectation value VEV to phi 0, one of it. Okay, the radial direction. And then I'm calling what is this? Well, how do I find this? I have to find solutions to these equations of motion. Let me just write them down. So I have to find v prime of phi 0, right? Now what I have is my v of phi, 1 minus half mu squared phi squared minus lambda over 4 factorial phi 4. I'm gonna ignore.
Lambda.
Yeah. I'm ignoring the indices, right? From this, if this is, well, I have to take a derivative. So I'm gonna get what? I'm gonna get mu squared phi. Phi mu squared minus lambda over 6. No, 4 factorial is what? 12? No, 24. 12, right? Yeah, 12. Phi 2 is equal to 0. There is one solution, which is phi equals 0, and then this 0 of this is then our solution. Good? No, it's phi 4, so it will be 6. Yeah. Okay. Right? So this sign is important. Previously, I took the other sign. All right. So when we do this, what we're going to do is we're going to take this vacuum and expand our field around this. So here's a fluctuation. Here's a fluctuation in the direction, in the radial direction, and then here's the in the direction of the that we picked our, I guess, in this direction, and then here are the perpendicular directions. All right, n minus 1 perpendicular directions. So you take the Lagrangian, you expand around phi naught, you're going to get a kinetic term for pi, kinetic term for sigma. There is a mass term for sigma squared, and then there's a potential term that looks like this. If you recall previously when we did this, well, here as well, you get a mass matrix, right? You always get a mass matrix. However, if you pick this sign to be plus, and the vev is given by the zero of this, the mass, the component of the mass matrix that have to do with this pi field will vanish. I'll explain that. So pi k is massless, O1 symmetry is spontaneously broken to O1 minus 1. All right, here's the derivation of why the mass matrix has these zeros. So we have a continuous global symmetry transformation that infinitesimally sends phi a to phi a epsilon delta phi a, right? This epsilon is a matrix in principle, right? V of phi a goes to V of phi a. It's a symmetry. It means that if you take a derivative with respect to, if you vary this with respect to del phi, it should be 0. This is what it means that under this transformation, this is what it means that you have a symmetry, right? Take a derivative with respect to phi b from this equation. There is this term, phi b, del phi b acts on this term, and then del phi b will act on this term. You could write it this way. All right. What is this? This is the mass matrix. Good. Now, when on the solution to the equation, at the minimum, this term vanishes. At the minimum, this term vanishes. So you have the mass matrix squared, right? This mass matrix squared times delta phi a equals 0. Good. Now, how do you satisfy this? There are two ways to do it. Either delta phi a is 0 or MAB is 0. Right? Delta phi a being 0 means what? Means that the symmetry is unbroken. But when delta phi a is 0, oh, sorry. Sorry. That's I said correctly. Delta phi a means that there have a symmetry. Right? Delta phi equals 0. Then when this is not 0, it means that for every mode that this is not 0, you get a 0 mode you get the 0 in the mass matrix. So this is a Goldstone theorem. For every unbroken symmetry, for every broken symmetry generator, you get a massless mode. Okay. Now, so what we learned is, we discussed this before, spontaneous breakdown of continuous symmetry implies that there are new massless scalar fields. There is a conservation of current, which holds as an equation, as an operator equation, right? However, what's happening? The ground state is not invariant under a transformation, right? So we have an Ambu-Goto Goldstone boson for every generator of the symmetry that's broken. Now, just did we go over this part as well? I don't think we did. So what is the ON current? Here's the ON current. You just use Noether theorem, the ON current. These are the generators of the ON Lie algebra, right? Is phi del mu phi minus this, what you would expect. Now, take this operator and stick it inside the following matrix element: 0 and a Goldstone boson. Right? Is it clear what I'm doing? So I'm just looking at the Goldstone boson next to the current. Why am I doing that? Because, well, because if I take a del mu of this, it has to vanish. Right? Okay, so take J mu A. As an operator, it's this thing, but when you look at the solution to the, when you look at the spontaneous symmetry breaking point, right? This is second order in phi. The first order contribution to it will be this term. Right? Because if you expand this, expand phi, put it phi 0 plus delta phi, this guy phi 0 plus delta phi, the lowest order term that pops out is this. All right, now put this inside this correlator. What do you find? You find that this correlator is minus I p mu ta phi naught of I e to the power minus I px. Good. More generally, what you obtain if this was if so here I put, well, what did I do exactly here? Oh, more generally, you can put some, you could organize these guys in terms of the representation theory of the group as well. So there will be J mu of A, pi of B. So there will be some phi A, B sitting here. That's just a minor comment for later on. Now, what is important is that if I take a derivative of this with respect to del mu, I have to get 0. All right, let's take a derivative of it. What is a derivative? It's just another p mu that contracts with this guy. Right? I p mu. So you find that minus p squared FAB e to minus IPX has to be 0. P squared FAB has to be 0. This is another way of proving Goldstone boson. This is equivalent to what we just wrote. Either the p squared is 0, which means massless mode, or FAB is 0, which means that the symmetry is preserved. Good? This is another derivation. Questions? All right. So what is spontaneous symmetry breaking and gauge theories? So that was a review of the ON model spontaneous symmetry breaking. Good. We said the gauge transformations are not real symmetries. It doesn't make sense to break the redundancy of the description. What we actually have are these non-local degrees of freedom. We have a one-form symmetry that we're breaking. This is intimately tied to topological order as well. But every time, what we're going to discuss now is the following. So when we had a global symmetry that we broke, the summary of it is the following: spontaneously break. When you spontaneously break it, for every unbroken symmetry generator, for every broken generator, you're going to get a massless mode, right? That's Goldstone boson. That's the consequence, right? Now we're talking about gauge theories. What happens in gauge theories? What happens is that when you have a gauge theory that's unbroken, you have long range force. You have a massless gauge boson. When you break it, it goes short range, and you end up with a massive gauge boson. All right? We're going to motivate this first using superconductivity. Consider QED, which is a U1 gauge theory, right? We can, what have been, to spontaneous break symmetry, it means that we're giving a VEV to the operators, to charge particles. So in QED, what is the charge particle. Fermion, electron. Can an electron get a VEV? Can a spinor get a VEV? The answer is no, because of the last two lectures. We discussed this, right? What does VEV mean? If you have a VEV for a spinor, it means that, sorry, non-zero. It means that you could interpret this as an overlap of a one spinor mode with a vacuum. We said that's nonsense. So you can't give a VEV to a one spinor. So an electron you cannot in QED, you cannot give it, you cannot have a condensate of electrons. Another way of saying is that it's a consequence of spin statistics, or the statistics of it. You can't have a condensate of it because your bosons form condensates, because they could sit on top of each other, but not fermions. Because of super selection sectors, we can't do this. So how can you spontaneously break the U1 symmetry of QED? What's that? Fermion pair, precisely. Why was this nonsense? Because this is not an observable. What is an observable? Psi. Good. So this is allowed. Oh, this is allowed. All right. So if you just study QED with a condensate like this, that's a BCS theory. That's a theory of superconductivity. These are called Cooper perps. Right? Now, why is BCS? Why is a superconductor? In what sense is a superconductor behaving like effectively describing a massive photon? And in what way is it long range? Is the force QED force now long range? So if what I just advocated is correct, there should be an effective mass for a photon for a superconductor.
That's why it doesn't feel the electric field.
It repels the magnetic field. That's what it is. So this is the Meissner effect. If you have some medium above the critical temperature, when it's not superconductor, there are no Cooper pairs, magnetic fields go through it. But the moment it becomes superconductor, it repels magnetic fields. Repelling means what? Meaning that when photons try to penetrate, they die exponentially fast. So if there's strong exponential decay in these directions, they go around it. Why should they go around it? Because you still have conservation laws. So the gauge boson is effectively massive. Here, the mass is so large. Well, the exponential is just exponential fast. Here, it basically means that it just dies pretty darn fast, right? It just means they cannot penetrate. And the force is short range because it cannot penetrate. Good. Was this familiar, at least somewhat? All right. So now that we know this, we say, what was this important about this psi? This is a first complex field. It's a boson field, and it has a U1 charge, which is 2Q, right? There is a global, previously when we discussed psi, we talked about the global symmetry. That's a Z2 symmetry. We are talking about different charges, right? A fermion has charge Q under the gauge theory. However, it has Z2 global symmetry that has to do with rotation by 2 pi. We still use the word charge for all of it, right? So if that is the story, let's just consider a simple model, the so-called abelian gauge theory. Just couple a charged particle to electromagnetic field, right? It's an effective field theory, if you wish. So, and let's study this. Now we could have a condensate of phi. So what are the gauge transformations? It's a complex field. So this is the U1 transformation, and the gauge will have to transform this way to cancel it. Right? And here's the potential. We need to arrange for opposite signs to make sure that spontaneous symmetry breaking happens. Here's a minimum of phi, but now phi is a complex field. So there's a phase. And this phase is a choice of gauge. Right? Previously, sorry, when we're talking about O2, when we drew this Mexican hat potential, previously when we picked our vector to be here, right? We're actually talking about, so we set the phase, for example, to be 0 or something. Then that was actually something physical. Here is all a gauge choice. But you'll see what happens. The solution that we're looking at is like this, and the mu is 0. That's the solution to these equations. Classical solution. Good? All right. So around alpha equals 0, we're going to expand. At alpha equals 0, phi naught is real. So if we look at the complex field as a real plus imaginary part, this is viewed as a fluctuations in the direction of this, and this is perpendicular. So this is the thing that's going to become similar to the massless mode of the, it's going to mimic the massless mode of Gould-Son boson. Mimic it. Right? Mimic it. Recall what J mu was. J mu, when we expanded it to the lowest order, is phi 0 del mu of phi 2. I can bring it back if you want. Well, okay, sorry. Let me go slower. So take V of phi, plug in this expansion, and expand. You're going to get, this is the kinetic, the covariant kinetic term for field phi. You're going to get del mu of phi 1, del mu of phi 2. You're going to get a mass term for a mu. This is your first indication of a massive gauge boson. Then you're going to end up with this term, which is phi naught a mu del mu of phi 2. Do you see where they come from? This is just J mu. Phi naught del mu of phi 2 is J mu, right? Let's look here. That's why I did the previous exercise. So forget about this. Phi 0 del mu of phi I is the current, J mu. So here's a mass term for the gauge boson, which is E squared phi naught squared. The phi 2 mode ends up being massless. If you take this literally and don't ignore the fact that this is a gauge theory, imagine that A mu's are all physical, and then this would be your Gould-Son boson. And this is the mass term for phi 1. There will be a mass matrix, there will be zeros, right? Phi, I repeat, phi 0 is a condensate of phi 1. Right? This field that ends up being massive, and this is plays a role of the gauge boson. All right. Now, there is this term. Well, this is a mass term. We also have to interpret this. Think about drawing a Feynman diagram for this term. It's a 2-point function that has a mu on one end of it, and on the other end has phi. Right? This is this term. This is the indication that your kinetic term is not diagonal. That's what it means. There's mixing. Right? If you have 2 degrees of freedom, phi 1 and phi 2, and your mass term looks like this, phi 1, phi 2, and 1, and 1, 1, and 1, 2, and 2, 1, and 2, 2. It looks like you have things that mix phi 1 and phi 2, right? It looks like something like that. So how would you go around this? You just diagonalize the matrix. Now, But this diagram, before you diagonalize the matrix, it tells you why the gauge boson is getting mass. Well, think about this gauge boson. Now it has this correction. This is the beauty of Feynman diagrams, right? So, and then it, like there was MA, and here's the extra term. If this was MA, this is a extra term that you get. But the massive boson remains transverse. So if you're worried about transverseness versus mass, we're going to come back to that and comment on it. Previously, we were saying that, remember that this was such a big deal for us that the gauge boson should not have a degree of freedom. Photon gauge boson should not have a transverse degree of freedom. This is a consequence of gauge invariance. And and it's important that it's massless. These are all related. I'm going to remind you of that argument, how these were related, how we use word identities to derive that, and see how spontaneous symmetry breaking goes around the argument. There was a fine assumption, very, very subtle assumption over there that I made that fails here, and it allows for it. Okay. If this, as I said, if this were global symmetry breaking, spontaneous symmetry breaking, phi 2 would have been the massless gauge boson. But in the gauge theory, what happens is that phi 2, in this example, right, this is phi 2, mixes with the gauge boson. So now it means that the initial gauge boson is not the degree of freedom you should be considering. The gauge boson is mixing with the field. Right? You have 3 degrees of freedom. You have the complex scalar field, phi 1, phi 2, and you had A mu. A mu has how many degrees of freedom? 2. Right? Once you spontaneously break the symmetry, you're going to be left with 4 degrees of freedom at the end. Again. Okay, we're going to do the count. But what is important is that if you end up with a massive vector field, the massive vector field will have 3 degrees of freedom, and you're left with 1 propagating extra degree of freedom. Sometimes people say that the gauge boson eats 1 degree of freedom of the boson, the scalar. That's what they mean. We're going to get there. So here's what the mass matrix is literally, just by expanding this Lagrangian to second order. I'm just taking out all the kinetic quadratic terms. Here's what it looks like. There is this term as a mass term for A mu. There is this term that mixes phi 2 and A mu. Of course, this guy. Phi 2 itself is massless. And then you have mass for phi 1. Is this clear? So once you do spontaneous symmetry breaking, these are no longer your degrees of freedom. Remember, every time we do spontaneous symmetry breaking, you have new effective degrees of freedom. Right? Some symmetry is working, they have effective degrees of freedom. You have to diagonalize this matrix and you'll see your degrees of freedom. But so first thing to notice is that phi 1 decouples. Right? And diagonalizing this, we don't need to touch this dude. This is 1 degree of freedom. So phi 2 and A mu, they have total 3 degrees of freedom, will combine to a massive gauge boson. This remains massive, and this is this mass. Just put it aside. Okay, so we're only going to work with this. Now, if you look at this matrix and you want to diagonalize it, the first problem you have is that this has a 0 mode. If you take A mu and phi 2 to be minus I over 2 k mu and phi 0, this is a 0 eigenvector of our mass matrix. You could check it explicitly. So this matrix, mass matrix, is not invertible. The fact that you have this 0 mode, it means that you have a pure gauge degree of freedom. That was expected. Right? That was totally expected. Can you see what is going on? We end up with a three vectors with these eigenvalues. Recall in our counting, why were there only 2 degrees of freedom for a massless gauge boson? There was 1 degree of freedom that was killed by our gauge fixing. We're down to 3. Then from that 3, there was the perpendicular, the transverse degree of freedom that's absent, right? That 1 degree of freedom, when we said is killed by pure gauge, that will be killed anyway, right? So what's happening is just something about the, oh, sorry. I'm misspeaking. The count, I discussed the count. There are 4 degrees of freedom, right? 2 of them remain intact. 1 of them is promoted, and then you can't separate them really. And then the other one is some pure gauge. We end up with a vector field with 3 degrees of freedom, and there's a gauge boson, and the massless vector field combine to get this. There is no Goldstone boson. However, the formulation of the theory, once you represent every gauge theory as a local theory, it's the same derivation, right? Right? But I do have a point here. Well, let me pause here because I will, yeah, let me pause here. Questions? The final spectrum of the theory is one vector mode that's massive and another scalar that's massive. You ended up with no massless modes. That's why I'm saying there are no Goldstone bosons. Good? That's the logic. The Goldstone boson was eaten by the gauge field to combine into this massive vector field. Questions? Now, actually, there is a gauge that you could choose to make your calculation a little bit nicer. This is the unitary gauge. This gauge fixing chooses phi as a complex field. It makes sure that phi is real everywhere. Right? I can always do that. When phi is real everywhere, it means that phi 2 is 0. Right? Good. Phi 2 is 0. Then when phi 2 is 0, I can just write down my action this way. There's a real scalar field here. You could repeat it, and it basically, it's a convenient language which you do not end up with terms like this. But I find this helpful to see what's going on, because this mimics closely Goldstone boson story, right? You could have done it this way. Some books do it this way. All right. So in remaining time, I'm going to pause and ask for questions. What I want to do is the non-abelian generalization of this. It's going to be more or less straightforward. There will be some extra features. In particular, there will be Goldstone bosons. There will be massless modes when you have non-abelian gauge theory. The reason is the following. Well, okay. Yeah.
How would one reverse the spontaneous?
Like, how would you recover it? Look at high, very, very high energies. So meaning what? Meaning that, so in this perturbation theory, right, what you're doing is you're saying that phi is phi naught plus some delta phi, and you expand it to second. That means that the amplitude of delta phi is always negligible compared to phi naught. But if you start trying to scatter things with large amplitude, this approximation is no longer valid. And if this is very, very large, you're actually working with the initial action. Right? It's this action. That's how you cover it.
So it really isn't related to the vacuum expectation. It really has to be very high energy such that you're spinning not around the minimum. Like you're scattering amplitudes there.
Correct. Yeah, I mean, yeah, exactly. So, I mean, where does spontaneous symmetry breaking come from? You have energies below. This is your potential. You have phi, and your phi's are below this, so you see spontaneous symmetry breaking. When your phi is large, now up here there's Z2 symmetry. Please.
Yeah, just because the Higgs vacuum expectation is like what 140 GeV, but I don't think we don't see the symmetry being actually reversed in the see that.
So I don't know.
So the vacuum expectation values like 140 GeV, we collide things at higher energies than 140 GeV, but we still see WZ bosons, right? In the end, we never reverse that symmetry.
Because I mean, if you start probing energy scales, if you start probing energy scales, the scattering phi's like Higgs that are very incredibly high energy, then you won't see it. Exactly. What will be that? What would that be? Actually, very good. Thanks for the comment. What would that give me a physical context that we know of, where we've actually somebody has done this experiment for us? We haven't done it. Big Bang. Right? So what is when people just like think about this deep at very, very high energies, right? The symmetry is restored. Well, I haven't told you what the symmetry breaking is. It's some symmetry breaking standard model that you end up with giving a VEV to the gauge field, and then the photon is released. Photon is free to travel. Right? Photon is a collective mode. Deep in the long time ago, early universe, spontaneous symmetry breaking, very, very early universe, spontaneous symmetry breaking. This spontaneous electroweak spontaneous symmetry breaking is irrelevant. But there's a moment that it actually happens in this history of cosmos, and that plays a role in cosmology. Right? Like, for example, another thing is that, like, we're trying to create quark-gluon plasma. This is deep in the UV of QCD, but also very, very early universe. It's also quark-gluon plasma at some stage, right? Yeah. Any other questions? Do you guys have the patience for me to go through the non-abelian case? It's a couple of slides. Is that okay? All right, because that allows me to. Next lecture, 2 lectures are going to be still. I'll review this in more detail again, but it should be pretty straightforward. So here's a non-abelian case. All I've done is that now I'm just taking these guys to be some scalar and some fundamental representation charged under the non-abelian gauge theory, right? F mu A squared, you understand the notation. Here is the transformation of the gauge field. Here's the transformation of the charged matter, right? And here's a covariant derivative of it. All right. So if I expand the covariant derivative, I'm going to get del mu of it, a mu A, ta phi dagger phi j, minus a mu this term plus this term. You wouldn't be surprised to see a mass term here. Right? This is that mass term we had before. The only thing that's happened is that there's an A and B appeared here and TAT. That's the extra thing. But every term has an analog up to these generators of the Lorentz of the internal symmetry. Every term has an analog for them, right? The current is still similar. All right, so what we're going to do is we're going to take phi 0 and write it as phi j of x, right? Phi 0 of j plus some fluctuating field. And this is a mu of a. Right? MAB, you repeat the calculation. Well, I mean, you don't repeat the calculation. You repackage this in this form. Just expand it. This is what it looks like. Oh, sorry. No, I said something silly. No, sorry. This is the kinetic term. This is the kinetic term. I said something silly. This is the kinetic term, right? But you have to expand the kinetic, this kinetic term. You have to expand the potential term, all of it, right? But okay, sorry. I want to highlight this term and this term. That's all I want to highlight that for now. When you repeat the calculation, you're going to end up with a mass matrix that looks like this. For every unbroken generator means TA phi 0 equals 0. You get this, sorry, you get this. You get the 0 eigenvalue for the mass matrix. And the analogous mixing that you find looks like this. So this, oh, I erased it. This mixing that I found, we're going to find it again between some phi A and the gauge boson. And it's because of this term. Not surprisingly, this is the current. So term by term, you could track the previous calculation with a bunch of extra generators of SUN or SON, or SON, doesn't matter. Once again, you find this term as a mass term, right? This contribution. But, and you also, and it could be repackaged this way, right? There's a mass that sits in front. It remains transverse. And if you calculate the J mu of A pi B, I showed this, I flashed this question before. This is what it looks like. Now I know what FAB is. I write explicitly. Right? Everything goes through nicely. But I want to comment, I think my last 2 slides, on massive photon and gauge invariance, or massive gauge bosons and word identities. Why? What did we assume previously in our argument, and how is this consistent with word identities? So what are the word identities? Gauge invariance tells you that Q mu contracted with the 1 pi propagator should be 0. That means that pi mu nu has to take this form, right? And then when you resum all of these guys, it becomes Q squared minus 1 over pi Q, right? So far, so good. These will still go through. Here is, if you recall, how the key idea was this, that photon had to remain massless, and it will be true if pi of Q has no poles as Q goes to 0. Right? What you would worry about is that, so if it's 1 over Q squared, in the limit of Q going to 0, you have the right pole, it's massless, everything is good. Right? So we insisted that this should not have an extra pole as Q squared goes to 0. Said differently, gauge invariance got all the way up to here, right? And then we said the masslessness had to do with the fact that as Q goes to 0, this is not vanishing. Sorry, this is not doesn't it remains massless. Good. So this argument is correct, but what's going to change is this part. What is this pi q? We calculate the pi q by doing this 1 pi diagram. If you repeat the calculation, you see that there were no poles as Q squared goes to 0 because this guy was massive. The fermions that run in the loop are massive in QED. That's exactly why. Now you have a massless mode that can run in the loop. If you have a massless mode, there are other massless excitations, it's possible to preserve gauge invariance and give mass to photon. Right? So rewind. What was this a summary of? Because I'm out of time. Previously, what we'd said was this. We'd said that gauge invariance means transverse modes. Transverse means that this diagram, this diagram has to be proportional to q nu minus eta mu nu q squared. That's transverseness, right? When we took that, so this is the transverseness. We did the one loop calculation. This is the expression we found. And then we found that this, as q goes to 0, has no poles, which means that the propagator is massless, remains massless. However, when you do the calculation in the presence of some other massless modes in the spectrum, it's modified. And I'm going to do that next time. I'm going to repeat this calculation next time and show you that exactly how it works. There is a pole. We can already see it, how there will be a pole. I mean, this is pretty straightforward. See, there's a pole. All right, any questions? Good. I repeat, homework 6 is posted, and we're going to go through 2 more lectures on the spontaneous symmetry breaking of gauge theories. I want to get this nice. Oh, no, sorry, one more, maybe 1 or 2. No, 2 more lectures. Then we're going to talk about symmetries, classical symmetries that don't survive quantumness. That's anomaly. Once we're done with those, the last part of the course is going to be standard-model particle physics, a success story. That's it. All right. Any last questions?